one thing I always do when I'm working on wires like that, if I see any wires I'm going to unplug that I think, well, I might get mixed up and not know exactly where that goes, it saves me a lot of time trying to figure it out if I mark it. So I got a lot of bottles of, they use it for putting paint on fabric. They call it fabric paint. They paint t-shirts, things like that with them. And I keep a bunch of those up here. You can get them all different colors, different shapes and stuff, and you basically squeeze it out. It's water based. You can wash it off with soap and water before it's dry. After it's dry, then you can run your t-shirt through the washing machine, so it stays on pretty good. But it's good for marking parts that you want to know where that goes and can I put it back there again. That's something I use for doing that when I'm doing something complicated like this. So I'm going to go ahead and disassemble some things here, and then I'll tell you a little bit about the cooling system there, what modifications I made to that. One of the things that I did, modifications that I've done, is to try to make this head operate like the blue head model does. One of the changes they made was to allow hot water to pass over this thermostat element. When the thermostat is closed, the water will still pass over it. What it does is these gray heads would gulp. What they call gulping. You might notice your temperature gauge as the engine's warming up. You'll see the temperature gauge going up. And then all of a sudden, the temperature gauge will start going down. And what happens is the element opens the thermostat, allows the hot water to flow out and into the radiator, and then cold water comes into the cylinders to refill them. And then the cold water makes the thermostat close right away. So what you see is, as the engine's warming up, you see your thermostat going up and down and up and down and up and down. And they call that gulping, is usually what they call it, at least with cars anyways, is what they call it. To fix that, I mean, Rotax put some different passageways. The way this head is cast is a little different on the blue head engine. But what I did to fix it on mine was something that I've seen on cars before that helps. Is there's two holes I drilled in this thermostat, one here and one over here, just small. They're about, maybe 1/8-inch diameter hole, something like that. And that allows water to pass through the thermostat whether the thermostat is open or closed. In other words, this thermostat will not shut off completely. It's always allowing a little bit of water to flow through there. That keeps water always flowing past this temperature element so that it doesn't gulp like that. It warms up slowly and gradually without doing any gulping and getting hot and cold and hot and cold like that. The other purposes it serves is that because this engine is mounted inverted, and I'll get into that a little later, but my radiator is mounted lower than my engine. The engine's actually the top of the whole cooling system. Actually, the water pump is the very highest point on the engine. So these little holes that are in the thermostat allow air to escape. When I'm trying to fill the system with coolant, I need a way for air bubbles to flow through there when the engine isn't warmed up yet, to get the air out of the system so that I can fill the cooling system. And these holes, these two little holes I put in there, do that. That's what their purpose is. So I've heard of people running these 582s without a thermostat, and I don't think that's wise at all. The engine runs fairly cool. It's something that needs a thermostat to keep it at the proper operating temperature, and the steadier you can keep it, the better off you are. So I would advise people to put the thermostat in there. They're kind of pricey, these thermostats. I mean, the thermostat element and the element in here and what it does is all the same as a car thermostat. And in fact, at one time I was debating making these thermostats by simply punching out the right diameter out of a car thermostat, and then it would fit right in there, and would be pretty easy to make, but I never got around to it. I think they want like $75 or something for a thermostat. It's just something crazy, but they could be made pretty easy if you get a car thermostat of the right temperature. The temperature, I don't know if you can see it or not, but there's a number stamped on here on the element that tell you at what temperature it opens. But if you're in doubt, put it in a pan of hot water on the stove with a cooking thermometer, and you can tell exactly what temperature it opens at. And that's a good way to test them to make sure they're working right. As long as the wife don't object to you using the stove. Mine's getting kind of fed up with that. You'll notice on this side the gaskets didn't stick to the head on this side, and this side they're stuck, but just barely. The gaskets fit in a groove in here. This is for the water jacket around the outside. It's just a rubber O-ring gasket, and the same for the head gasket. It's just rubber O-ring. That's the head gasket. The head gaskets, you can purchase these things. You might have to order them, but you can get them at a O-ring supply house. Can send you a gasket like that. There's nothing special about them. I mean, if you can get them in Viton, is a good idea, because there is some heat involved here, but it's really not necessary. This head fits flat against these cylinders, so there's just almost no clearance between them at all. It's going to be a thousandth or two at most, so it's not quite like crushing a head gasket. These head bolt screws are torqued to a certain torque, but it really isn't necessary to do that kind of things when you don't have a head gasket that you're crushing or compressing in there. It's just not necessarily needed. Anyways, this engine has about 300 hours, just a little shy of 300 hours. I'm doing it this winter mostly because of something to do, I guess. Got the COVID going around. So you can see it's not very carboned up at all. It's very clean inside. Since the last time I did this for 300 hours, I'm not getting much carbon at all. I'm using a Pennzoil It's a water-cooled oil for outboard motors and two-cycle engines. Now they've changed their formula. You can't get the air-cooled stuff. It's actually a mix, a synthetic hybrid. It's got mineral oil and synthetic mixed together, and it seems like it's doing pretty well. It certainly isn't making much carbon. Let's see if I can run a piston up here for you. And there you can see the piston. Now these clean areas are probably where there's transfer ports, and it's got gasoline blowing across that carbon, and apparently it doesn't want to stick there. So gasoline must be cleaning off the carbon or something. But at any rate, the pistons will polish up real easy, and there's not really that much carbon on them. They'll probably have more carbon on the back side of the piston. When I take the piston off of the rod, there'll be more carbon on the back side than there is here on the top, because my engine's inverted, and every time you shut it off, the oil runs down into the cylinders, or on the back side of the cylinder, and runs down into the piston, into the bottom of the piston behind this piston dome, and puts a little puddle of oil is going to accumulate in this piston dome when you shut it off, which of course is probably pretty hot. It's probably the hottest part of the engine, and it kind of cooks it in there, so you do get carbon buildup on the back side. That's probably more carbon back there than there is on here. The other thing I wanted to tell you about, let's see, is in here you'll see a rubber donut. And let's see if I can turn that there. This is the rubber donut that drives the gearbox. I put a paint mark in here. At the point where this paint mark is, both of these pistons are even, as you can see. Now I put two paint marks on there because there's two places that could stop where the pistons would be in this position. The idea of that is if I'm going to store the airplane, say I figure, well, I'm not going to be back here for a couple months to run this thing. I want to try to keep the transfer ports closed as much as possible so I don't get so much oil running down there. Now with this engine, they have a exhaust port that opens pretty early on there, which is right here, but that's not going to bother you. What you want to have is those transfer ports closed in there. So by putting this paint mark on there, I can turn the propeller on here to get both pistons evenly spaced, and that closes the transfer ports so that oil from inside the crankcase doesn't run down. You know, when it sits in there for a long period of time, like I say, it all runs down towards the cylinders and the piston. It doesn't leak into the head because it'll make a puddle right here in the head, which will make it pretty darn hard to start because it'll all be flooded with oil in there. So inverted engines can have a problem with oil in the plugs when they just sit. And now usually in the spring, after it sits all winter, I will take and remove the spark plugs and clean them in the spring. Both plugs, I clean them and let any oil that is in here, because some of it will get past the piston rings. I mean, the oil's really thin stuff, and it's slowly oozing and moving all the time in there, and it's going to come down in here and go into the head. So that's the reason why I put the paint marks in there. And like I say, there's two paint marks because there's two positions, you know, where I can set that engine. And all I do is turn the prop when I shut it off and watch for this yellow paint mark. That's all I do. And that makes sure that those are not going to allow oil to go down into these cylinders because I have an inverted engine. You wouldn't have to worry about it if your engine's right side up. I don't think there's really much reason to do that, but it's because my engine's inverted that I want to do that. This is the water pump impeller, the back side of the impeller, which I just pulled off there. There's a washer and a serrated, what they call D drive. It looks like a D because there's a flat on it that fits on the flat that's on this shaft. And this is one of the design errors that they had in this engine, in my opinion anyway. But the main design error, which is the reason I think that they painted the heads blue, because the color blue has nothing to do with it. It just makes it so you can stand there and look at an engine and say, well, that head's been modified to get the water flow through the head right. But it also tells you that it has this modification, which is this rotary valve shaft. This is the opposite side of the engine from the rotary valve. It has a lip seal on here for sealing the coolant in there behind this water pump impeller. All water pumps have some sort of a seal behind the impeller, and in this case they just used what they call a lip seal. Now lip seals are what they use on the crankshaft ends and in the middle and everything else. They use these, and you'll see these on a lot of engines to keep the engine oil in and so forth. However, it's to keep oil in, it's not to keep a lot of pressure in there. Well, then they started using a pressurized cooling system, and they have a cap. I'm not sure, I think it's 14 pounds or something on one of these when you use the Rotax radiators, because the Rotax radiators are very small, and the pressure puts pressure, of course, on this rubber and pushes the rubber into the shaft. Their first attempt at correcting this was, I think the first ones had a larger diameter shaft, and they cut this diameter down to reduce the surface speed, because what happens is this rubber will wear a groove in that shaft. Rubber will cut steel, even heat-treated steel. Believe me, I know I've tried before, and it always does. It doesn't wear well on there at all. You need like Teflon or something might work, but to have rubbing against even a hardened piece of steel, eventually it's going to wear through, make a big groove in there. So what they did was they modified this on the Bluehead engine to use a mechanical seal. And that's what most water pumps, a water pump on a car or something like that, have. Anything that's using any kind of pressure has to have a mechanical shaft seal rather than one of these rubber lip seals on there. And I'll show you how the mechanical shaft seal works here in just a second. Now this is a mechanical shaft seal, which you can see consists of a spring and a movable seal face, which most always, either the part that moves or the part that's stationary is going to be carbon. Most of the time it seems like the part that moves is carbon. This has a carbon face right here on this face of this thing. The spring pushes this carbon face, which is lapped. It's very precise, and that runs against this, which is a seal face that would be on the back of the impeller, and you'd have this seal face go against there like this, with the spring pushing it against there, against the impeller. It seals by closeness of fit. In other words, this plate has been lapped, and it's lapped so flat, as is this carbon, that those two pieces, when they come together, if you put any tension on them at all, water can't get past there. It can spin, but water doesn't leak. That's in what's most automotive water pumps that you're ever going to find. That's what they used, going clear back to the 30s, in one way or another. It changes depending on where the spring is. Some of them have the spring on the impeller. Some of them have the spring in the housing. Most of the time that's where the spring is, in the housing, and the carbon face is usually in the housing. So this piece would go in the water pump housing. It would fit into a bore that would be here. Now you have to understand, this is a much bigger seal than what you'd use on a little tiny impeller like this. This is all miniature stuff, but that's what it would use, something like that in there. And then this seal face would fit into a bore that's bored in the back of the impeller. It'll always be extremely flat. They use cast iron. This one looks like it's brass. They're usually going to use something that won't rust or corrode. Cast iron, brass, or the best ones I like are stainless steel. It's pretty good for that. This one, you'll notice, has like a rubber seal on the outside of it, so it fits tightly in a bore in the back of the water pump or in the housing, and that seals the water from getting around this piece. So it can't get around the seal by going on around the outside of it. So that's just a stationary rubber seal that's just like a gasket or something. The spring, of course, should be stainless. If it's made out of something else, you could get rust on the spring, which of course eventually it would break, which is one reason why you always want to have antifreeze in your coolant system so that things don't rust in there, because water is going to rust things, especially hot water. So these things are pretty dependable, and most cars go 100,000 miles with no problem with the water pump, even though they're spinning really fast. So that's the difference, and that's what they went to on the Rotax 582. I don't know what it looks like because I've never had a Bluehead 582. I just know that they changed it. I don't have any parts to show you exactly how they did it because I don't know. The other thing I'll tell you about is there's a weep hole that's designed behind this seal. If any water ever got past this leak seal, or this lip seal here, if any water gets past that, it goes into a space behind there where there's another seal behind it that seals in the oil for the rotary valve in that box. But there's a gap, a space between these two seals, and from there's a drain that comes out, and it comes out into this slot. It's gonna, if it leaks out, it's going to come out of this slot right here, which is pretty hard to show you from here. Not much light here, but there's a slot in there where the oil can come out. And one of my modifications is that Rotax plugged up that slot. They did that because I think they'd have brand new engines and a little bit of coolant would come out, and it looks like it's coming out of this gap between the cases here, and people would complain about it. So the story I got is that's why they plugged that hole, when all they did was drill and tap a hole in there and put a set screw in it with Loctite, and that way it can't come out of there. But when I get the cases apart, I'll show you that particular feature on here. But most people are never going to take apart their cases. I mean, taking off the cylinders and everything, that's pretty easy. The rest of this, you have to remove the gearbox, and you have to remove the magneto and everything on this end, so that'll be a bit of a project. But being as I'm really going through this engine and checking everything, why, that's what I'm going to do. But I just wanted to tell you about that hole, because I'm going to be showing you that again as to what that is, and all water pumps will have something like that. Even if you have one with this dynamic seal, there'll be an area in there between this seal and the bearing, whatever's holding the shaft. There'll be a gap in there, and that gap will have a hole to the outside, and that's how water gets out of there. Let's see, one other thing I wanted to tell you is this. This is another modification I made. Because my engine is inverted, that makes this water pump the highest point on the system, and I don't use any pressure in my coolant system. And that is why I can get away with so many years on this lip seal, because the water is not pressurized in there. This engine is cooled like a Model A Ford or something. There's no pressure cap. If it was to get to the boiling point, it would just start boiling water until all the water was gone. And anybody that ever boiled water in a paper cup, a lot of people would do that around a campfire just to show people what it could do. But you can't get the container hotter than 212 degrees, so the paper cup won't burn up as long as there's water in there, because the water is keeping it cool, because it turns to steam, and that's as hot as that water is going to get is boiling, which is 212. Unless you're up in the mountains or something, it would be considerably less than that. So altitude's going to have an effect on it. So this system probably wouldn't be too good if I was going to really try to fly over 10,000 feet or something. It might give me trouble, but I don't use just water in it. I use straight coolant. I don't mix any water with it. It's a straight coolant, which has a much higher boiling point. So anyways, this fitting that I put in here, you'll notice there's a screw here too, on this side of this water pump housing, but I put it on here so that it's going to be the highest point on the engine, and there's always going to be some water coming out of this tube. A little bit of water comes out of there, and that goes back up into my coolant recovery tank, and that is the way it self bleeds. If any air gets in that system, air, steam, anything, it's going to go up this tube eventually and back into the coolant recovery tank, where hopefully it'll get condensed. But that's what that is the air bleed for the whole system. This is it right here. So I thought I'd better show you that and make note of that's the way this works. But that's simply because this is an inverted engine. I'll show you something else here too while I'm at it. On the head, if your engine sits upright in there, you've got a screw here on the back and the front, because the engine could be tilted a little bit one way or the other, to make this the highest point in the system if your engine is setting upright. And that allows you to bleed the air out, and usually there's a fitting in there, and they have a way of getting the little hose on there that gets the air out of there and goes back into the coolant recovery tank. These copper tubes that you see on here, that's something I put on there. I drilled and tapped some holes in this head, which conveniently they had a boss right there where I could do it. Oops, don't want to drop this thing. And I drilled and tapped that, and I think I drilled and tapped this one too to put my sensor in there. But these holes are drilled and tapped here for the coolant from my cabin heater. It has hot water cabin heater, which I made out of a heater core. It's a heater core and a computer muffin fan, and it just circulates the air over and over inside. So that's what warms up the cabin on the plane.